In the given equation, it is asked to diagonalize A, which is A given as 1, 2, 3, 0, 2, 1, 0, 0, 3. So A is given as this one, such that D is equal to P inverse AP, where AP is invertible matrix and D is the diagonal matrix. To prove this condition, we need to find the characteristic equation from A, and by solving the characteristic equation, we will have the eigenvalues. By using the eigenvalues, we will have the eigenvectors and also the diagonal matrix. Then after using those matrix, we will satisfy this condition. By satisfying this condition, we can prove this condition. Okay, so let's find the characteristic equation. To find the characteristic equation, the rule is det of A minus lambda I, where I is the unit matrix in 3 cross 3 order, equal to 0. From this characteristic equation, we will have, simply we will minus the lambda from the diagonal element. So 1 minus lambda, 2, 3, 0, 2 minus lambda, 1, 0, 0, 3 minus lambda. So we have this characteristic equation equal to 0, which give us 1 minus lambda into 2 minus lambda into 3 minus lambda, and the remaining part, if we determine this remaining part, we'll have 0. Okay, so when you determine this part, we'll have 0, so equal to 0. So from this equation, we have lambda is equal to 1, 2 and 3. These are the eigenvalues. Okay, these are the eigenvalues. We'll use these eigenvalues to find the diagonal matrix. The diagonal matrix will be simply 1, 2, 3, and the remaining elements will be 0. So this will be the diagonal matrix. As we have taken this order, we have to find the eigenvectors in the same order. So for lambda is equal to 1, let's eigenvector is equal to P1. Okay, so to find the eigenvector, the equation will be A minus, in the place of lambda we have to put 1 and the unit matrix of 3 cross 3, and this will be P1. This is the cap P1. Okay, equal to 0. So simply you will put 1 in the place of lambda in this equation. So 1 minus 1 will be 0, 2 minus 1 will be 1, and 3 minus 1 will be 2. So we'll put that this way. So we have 0, 2, 3, 0, 1, 1, 0, 0, 2. So this is the matrix. And P1, we can write this P1 as small p1, small p2, small p3 equal to 0. From this matrix, we have the system of equation, which is 0, p1 plus, these all are small p1. Okay, this one and this one is only the cap p1. So 2 small p1 p2 plus 3 p3 equal to 0, equal to 0 p1 plus p2 plus p3 equal to 0. These all are small p1 and p2 and p3. So we'll use the method here, that is this one. We'll erase this part and we'll multiply this one to this one, and we'll multiply this one to this one. We'll write it here, and when we do this part, we'll erase this part and we'll perform the same one. So to erase this part and perform this one, it will be 2 minus 3 and this will erase, and this will be 0 0. So this will be 0, and when you erase this part, this also will be 0. So from here, if we consider this equal to k, we have p1 is equal to minus k, p2 equal to 0k, p3 equal to 0k. From here, if we take minus k common, so the cap p1 will be k1, where k1 is minus k1. Okay, we have taken minus k equal to k1, so inside we'll have 1 0 0. Okay, so this is the eigenvector. Next we have to find out for lambda equal to 2. Let's the eigenvector as cap p2. So we'll have a minus 2i into cap p2 equal to 0. So from here we will perform the calculation, and we have minus 1 2 3 0 0 1 0 0 1. So we have this one, and we can write this small p1 small p2 small p3, which is equal to 0. From this system of equation we can write this one minus, this will be p1 small p1 plus 2 small p2 plus 3 small p3 equal to 0. And also from here we will have p3 equal to 0. Okay, so from by performing the calculation we will have p1 equal to, this is p2, right? So p2 will be, cap p2 will be 2 1 0 k as a constant. So the p2 vector will be this one. So for lambda 3, let's take the eigenvector is p3, cap p3. So we'll have a minus 3i p3 equal to 0. From this equation we will have minus 2 2 3 0 minus 1 1 0 0 0, and p3 can be written as small p1 small p2 small p3 equal to 0. So we have the system of equation from here. This will be minus 2 p1 plus 2 p2. These all are small p1 p2. Okay, so 3 p3 equal to 0, and this one will be 0 p1 minus p2 plus p3 equal to 0. By solving this equation, we'll have cap p3 equal to 5 by 2 1 1. Simply when we solve this equation using this method, that is equal to minus p2 by equal to p3 equal to k, we'll simply have this one. This will give us 5, this will give us 2, this will give us 2. So when we take 2k common and write it as 2k as k1, we will have 5 by 2 1 and 1. Okay, so now we have the eigenvectors as well as the diagonal matrix. So the diagonal matrix, which is 1 0 0 0 2 0 0 0 3, this is the diagonal matrix, and we have the, this is not x, let's, this is p, capital P. We have the eigenvectors, which is 1 0 0 2 1 0 5 by 2 1 1. So we need to find P inverse. To find P inverse, we need to find the adjoint of P by the determinant of P. So to find adjoint of P, for adjoint of P, we have to calculate this part. So first of all, we'll give the sign plus minus plus minus plus minus plus minus plus. So we will take this part, we'll write it as this way. When we'll take this part, we'll write it as this way. When we'll take this row, we'll write this column. Okay, so we'll take 1. For 1, we'll erase this part, and this part will have 1, and this will 0. 1 minus 0 is 1. Again 2, this part will be erased, this part will be erased, so 0. So 0. Whenever we'll move this way, we'll write this way. So for 5 by 3, we'll erase this part, and this part will be 0. Again 0. So then the second row. So from second row, we'll have 2, 1, 0. From the third row, we have, so this will be minus 1 by 2, and this will be minus 1, and this will be 1. So from that, we have 1 minus 2 minus 1 by 2, 0, 1, minus 1, 0, 0, 1. So this is the adjoint of P, and if we find the determinant of P, we'll simply have 1 into 1 minus 0 plus the remaining one, this will be minus, the remaining one will be 0 plus 0. So determinant is 1. So we have the inverse, which is adjoint of P by P. If we divide this one by 1, we'll have this one. So 1 minus 2 minus 1 by 2, 0, 1 minus 1, 0, 0, 1. So this is the inverse. So now we have P inverse P and as well as D. So we have these three will satisfy the condition. This is the condition. This is the given condition. So we'll write this right hand side and we'll prove this is a diagonal matrix. So right hand side is P inverse P, P. So this is P inverse is 1 minus 2, 1 by 2 minus 1 by 2, 0, 1 minus 1, 0, 0, 1. And A is 1, 2, 3, 0, 2, 1, 0, 0, 3. And P is 1, 2, 5 by 2, 0, 1, 1, 0, 0, 1. So this is P. So you can also see from here, this is P, this is P inverse, and A is given. Okay, so we have this three matrix. First of all, we will perform the multiplication, matrix multiplication with this two. So we'll perform the matrix multiplication. We'll multiply this one with this one, this one with this one, this one with this one, and we'll plus them. So we have 1 plus 0 plus 0, and this one with this one, we'll have 2 minus 4 plus 0. From this one with this one, we'll have 3 minus 2 minus 3 by 2. And again with this row, from this 3 row, we'll have 0 plus 0 plus 0, 0 plus 2 plus 0, 0 plus 1 minus 3, 0 plus 0 plus 0, 0 plus 0 plus 0, 0 plus 0 plus 3. So simply we have to perform the matrix multiplication. Simply this row with this column, this row with this column, this row with this column, this one, this one, this one. Simply we have to perform the matrix multiplication. Now we have this multiplication and write this one as same. So we have 1, 2, 5 by 2, 0, 1, 1, 0, 0, 1 and this one. So now from here, when we calculate this part, from this part we have minus half. So we can write this 1, this will minus 2, this will give simply minus half, minus 1 by 2. This will be 0, this is 2 and this is minus 2. This will be 0, 0 and 3, 0, 0 and 3. So again we have to perform the matrix multiplication with these two matrices. That is this one 0, 1, 1, 0, 0, 1. So let's perform the matrix multiplication here. That will be 1 plus 0 plus 0, 2 plus minus 2 plus 0, 5 by 2 minus 2 minus 1 by 2, and this will be 0 plus 0 plus 0 and 0 plus 2 plus 0, 0 plus 2 plus minus 2, and from the third row we'll have 0 plus 0 plus 0, 0 plus 0 plus 0, 0 plus 0 plus 3. This we have. When we calculate this part, we have 0 from this part. So we have 1, this will be 0, this will be 0, this is 0, this will be 2, this will be 0, this will be 0, 0, and this will be 3, which is equal to the diagonal matrix. You can see this is the diagonal matrix which we find. So from this here we have this satisfied condition. So we proven the condition which is D is equal to P inverse A P.